Okay, so thanks a lot for the invitation and for giving me the opportunity to give this talk. So, okay, now it should work. So I believe the true purpose of this talk is to show that the elementary quadratic relations among the holomorphic periods of CM abelian varieties of the form θ1, θ2 equals θ3, θ4 are really at the core of the theory and appearing in several ways. So I tried to explain this. I start by the way I encountered this kind of relations. So it's a very basic thing. You have a complex vector space, and you say that a B Q-bar structure on this complex vector space is just the data of two a priori different Q-bar structure, W1 and W2 on V. So you just find two bases and you look at the Q-bar vector space generated by this Q basis. And when you have a subspace, V prime of V, you say that it's B Q-bar if it's Q-bar for both the structure on W1 coming from W1 and one coming from W2. So we will do even simpler thing. We will be interested in the case where you have a B Q-bar subspace of dimension 1. So in this case, you define very naturally a complex number up to multiplication by an element of Q-bar star by saying that on V prime, you can find two elements, E1 and E2. E1 in the Q-bar structure W1 and E2 in the Q-bar structure W2. And then the scaling between the two elements is some well-defined number modulo the multiplication by an element in Q-bar star. And so you call this a period of V for this B Q-bar structure. And in the talk, I will be interested in a very simple thing. The notion of a B Q-bar structure, which is split. So it just means that the vector space, the complex vector space, is a direct sum of B Q-bar subspaces of dimension 1. So it just means that the space is a sum of, in two ways, the sum of C, Ej, C, Fj, and the two bases are related by multiplication by some periods. And so in this situation, you just say that θ1, θn is a complete set of periods of V for W1, W2. Okay, so it's a very basic theory, and there is just a remark we can do. So when you have a split B Q-bar structure with a complete set of period θ1, θn, you may consider two different situations. The first one is if all the θi are really different, so up to multiplication by Q-bar star, then there are only finitely many B Q-bar vector subspaces. It's just the linear combinations of the one-dimensional one. But if, for example, all the θi are equal, then any subvector space W for of V, which is Q-bar rational for one structure, is Q-bar rational for the other. So it means that in this case, you have infinitely many B Q-bar things. So the only thing for the moment we can keep in mind is that we can detect equalities between periods by knowing that there are infinitely many B-Q-bar vector subspaces. Okay, so it's a principle that we can use. So the first instance of this kind of thing is coming when I start with a complex CM abelian variety of dimension G. So in this situation, A is the extension to C of an abelian variety defined over Q bar. And I will endow the universal covering of abelian variety by a BQ bar structure. So the first one is coming from the fact that the abelian variety is defined over Q bar. And I say that C power G is just the extension to C of the Lie of A Q bar. So this, I call it the arithmetic Q bar structure. And the second one is more related to complex multiplication in the sense that when you do complex multiplication, the abelian variety is written as usual as C power G divided by a lattice of the form Z power G plus tau Z power G. But now tau is really a matrix with coefficient in Q bar. And so the Q bar space generated by a basis of gamma is really a subspace of dimension, a Q bar subspace of dimension G in C power G. And we call this the geometric Q bar structure. Okay. And okay, so how it's related to the usual theory of periods. If you start with an end of A tensor Q eigenbasis of holomorphic one forms, then the quantities theta j equal the integral over omega over gamma of omega j is up to multiplication to Q element in Q bar, not depending on gamma. And so it's an observation by Shimura, I guess. And then you can find a gamma such that these numbers theta j are non-zero. And so you have well-defined holomorphic periods of A. And if you look at the complex conjugate of the omega j, you have almost the same information because the integral of this complex conjugate are the 2 I pi divided by theta j. So this, you call them the anti-holomorphic periods of A. And you can check easily that the BQ bar structure on C power G defined above is split, and the period, the complete set of periods of this BQ bar structure is just theta 1, theta 2, theta j. Okay. So as I will speak a lot about
I'm sorry. So what were the two structures? So you in the previous examples, what were the two Q bar structures?
I mean, one is coming from the fact that on the Lie algebra of abelian variety, you have a Q bar structure because the algebra is defined as a Q bar.
Yeah, I meant in the next slide. You have the periods. Oh no, you were just saying that these were the periods for the two structures. Okay.
Yeah.
Okay. Can so I've got a related question. So if you look in the moduli space of abelian varieties,
I will come back to this.
is it related to the two Q bar structures you get on the fiber and on the projection?
Okay, it will be part of the talk. So
okay.
Okay. So okay, but I want to remind you some properties of holomorphic periods on CM abelian varieties. So the important input is the Mumford-Tate group of the abelian variety, which is a torus in this case. And it's known that the holomorphic periods are transcendental numbers. It's also known that if you take the product theta I, theta j, divide by pi, it's also transcendental. It's not known if you don't divide by pi, I guess, but I mean, the most important theorem in that direction is that if A is simple or square free, there is no Q-bar relations between the holomorphic periods. So if the Q-bar vector space generated by the theta I is of the dimension of abelian variety, then the transcendence degree of all the periods or of 2i pi and the holomorphic periods is bounded by the dimension of the Mumford-Tate group, this algebraic torus, and this torus is of dimension at most g plus 1. And Grothendieck period conjecture predicts that this transcendence degree is the dimension of T. Okay, so well, in this game, to understand the holomorphic periods, or all the periods, you have to use the comparison isomorphism between the H1 de Rham and the H1 Betty once you extend the scalar to C. And this isomorphism is a point of a period torsor tau, and this period torsor can be identified to a subgroup of the Mumford-Tate group. And if you choose correctly your basis, the comparison isomorphism become a diagonal matrix with entries theta 1, theta g, 2i pi divided by theta 1, 2i pi divided by theta g. And it's inside the Mumford-Tate group. And this Mumford-Tate group is inside a maximal torus of GSP of H1 AQ. And if you have two roots of this maximal torus acting on the Lie algebra of the symplectic group, which have the same restrictions on the Mumford-Tate group, when you take the evaluation at this point beta, you compute it, you find theta I, theta j, and theta k, theta l, and this gives you an elementary quadratic relation. So sometime when T is smaller than the maximal torus, you may hope to have this, you may have this kind of relation. And another remark is that if Grothendieck periods conjecture is true, beta is a generic point of MT of A, and you cannot have other relations of that form. Okay, so now from another perspective.
I'm sorry. Could you say in 2 words what's the Mumford-Tate group?
The Mumford-Tate group, I mean, you have several definitions, but an abelian variety is given by the Hodge structure and associated to any, say, Q Hodge structure. You can associate an algebraic group. So even in Tanakian languages, or just by doing the definition of a Hodge structure. So if a Hodge structure is the action of the Deligne torus on a vector space, you can construct a smaller algebraic group defined over Q such that this morphism factorized through this group. But you have to know that associated to any Hodge structure, you have such a Mumford-Tate group, any Q Hodge structure, And for CM abelian varieties, this Mumford-Tate group is a torus. Okay, so now when you do the way usually you produce relations between periods, or say holomorphic periods, is to construct algebraic cycles. But in fact, when you do abelian variety, by Deligne result, any Hodge cycle is absolute. And in fact, the Hodge cycles are providing relations between periods. So in the case of CM abelian varieties, all the relations provided by Hodge cycles are elementary in the sense is that they are just up to multiplication by an element in Q bar star, the equality between two monomials in the periods. So typically, theta 1, theta 2 is theta 3, theta 4, or theta 1, theta 2, theta 3 is theta 4, theta 5, theta 6, these kind of things. So in principle, you expect that there are no other basic relations than this one. So if you look at Grothendieck periods conjecture, you have the relations given by the Hodge cycles on powers of A, if you want. You have elementary relations which are given by equalities between two monomials and if, okay, I don't speak about Betty Durham, it's not important here. If Grothendieck periods conjecture is true, it should be the generating all the algebraic relations. You should not find, okay. So the theorem we had on this part with Ziyang-Gao is the following. If you have a CM abelian variety, say associated with a CM algebra or a CM field, if you want, then so I want to say that essentially all the relations between the holomorphic periods are coming from quadratic relations, elementary quadratic relations. So it's not fully true, but what is true is that you can find another CM abelian variety, so such that the endomorphism of this abelian variety has the same Galois closure, or have a Galois closure contained in the Galois closure of endomorphism of A, and such that if you look at all the non-trivial Hodge relations between holomorphic periods of a product A cross B, then they are generated by the elementary quadratic ones. So relations of the form theta I, theta j equals theta k, theta l. And they are induced, in fact, by two Hodge cycles on a product like A cross B. So this means that, so it's not true that you can find some example where you have an abelian variety for which there are no quadratic relations, but you can find a companion, a neighbor, and if you take the product, then there is a way the holomorphic periods are mixing in some way such that all the algebraic relations between the periods of the product are generated by these elementary relations. Okay, so I will come back to this a bit later, but I want to speak about the this B Q-bar structure now on Shimura varieties. So,
I'm sorry?
yeah.
Just in your result, A times B is going to be what kind of abelian variety? Will it be split? How do you say simple?
No, B, A cross
A times B, A times B.
So it's almost by definition not simple, but it's generally not simple at all. Yeah, but yeah, I mean, B is generally, yeah, it's in general quite. I mean, B will have endomorphism by some ring or some field, if you want, and the Galois closure of first endomorphism ring and contains the Galois closure of the second. It's the only thing you would know, but
Okay, thanks.
okay. So when you have a Shimura variety, so a Shimura variety is given by a couple, an algebraic group of a Q and an Hermitian symmetric space. So an Hermitian symmetric space is a quotient of the real point of this algebraic group divided by a maximal compact of this group. I write it K infinity. And S is the quotient of this Hermitian symmetric space by an arithmetic lattice. So I would like to explain that on the tangent space of this kind of object, I have naturally a BQ bar structure, and okay, we'll see. So you look at the uniformizing map from this Hermitian symmetric space to the Shimura variety. And the first point is that a Shimura variety is, in general, a quasi-projective variety, and it has a canonical model of a Q-bar. So it means that if you look at a CM point on S, this CM point is in fact defined over Q-bar. So you see that if you look at the isomorphism between the tangent space of a point above the CM point on X, then you can construct a Q-bar structure on T0 of X by saying that you have a natural Q-bar structure on the tangent space at the Shimura variety at the CM point. And as previously, I call this the arithmetic structure. So there is a second structure. So it's more, there are several ways of producing it, but the way you construct Hermitian symmetric space or even symmetric spaces is to say that you look at the Cartan decomposition associated to a point of your symmetric space. So somehow your symmetric space is parameterizing all the possible such Cartan decomposition. So, but this, okay, this is a real Cartan decomposition. And when you extend the decomposition to C, the M part of the Cartan decomposition further decompose in two parts, MC plus and MC minus 1, which are sub-algebra and even sub-abelian Lie algebras of GC. And the holomorphic tangent space of the Hermitian symmetric space in this situation is the MC plus part. And if you take the intersection of MC plus with the Lie algebra of the group G extended to Q bar, you can check that this is a Q bar subspace of the holomorphic tangent space. So this is the second Q bar structure, and you call it the geometric structure. Okay, so it's yeah. So somehow it's a bit like in the abelian variety case. This structure is more related to the way G of Q acts on the symmetric space, and the first one is most related to the fact that the Shimura variety is defined over Q bar, and the CM point also. So the statement we have in this direction is the following. So if you look at these two Q-bar structure on T0 of X, the arithmetic one and the geometric one, it's split. So it means that the space is direct sum of one-dimensional subspace with the two structure. So the way it works is quite simple. So if you look at the Mumford group of the CM point, the abelian variety corresponding to the CM point you're working with, you embed this Mumford group in a maximal torus containing T. Sometimes T is already a maximal torus, and you look at the root system. So this maximal torus acts on the Lie algebra of your group, and when you just look at the part of the Lie algebra MC plus, you can decompose it as root spaces. So the usual theory tells you that these root spaces are one-dimensional. And the only thing I add is that they are in fact BQ bar. So you look at the usual root space decomposition of the MC plus part of the Lie algebra GC, and the root spaces are in fact BQ bar. And to make things very concrete, if you look at the moduli space of principally polarized abelian varieties of dimension G, okay, in this situation, your group is naturally the symplectic group, and the symmetric space is the Siegel upper half place, and this is just the set of complex matrices which are symmetric and with imaginary part strictly positive. So in this situation, a CM point corresponds to a CM abelian variety, as in the previous part. And so we saw that a CM abelian variety, you could associate some holomorphic periods and a Mumford group, and the same, you're in the same situation. And the result is that the period of the split BQ bar structure at the tangent space of the CM point is really the sin 2 of the split BQ bar structure you had on the tangent space of the abelian variety, almost twisted by something, in the sense that the periods on T0 of Hg are just the product theta I, theta j divided by pi. And if you look at the root space corresponding to the root epsilon I plus epsilon j, which is really the roots inside MC plus, then the associated period is theta I, theta j over pi. Okay, so if you look at the tangent space at a CM point of a special subvariety, it's very easy to check that the tangent space of such a variety will define a BQ-bar subspace. So, there are, as I said at the beginning, you may have two very different two different situations. One situation where all the theta I, theta j are distinct. And in this case, you will have only finitely many BQ-bar subspace of on the tangent space at your point of AG. Or you have a lot of, or you have some equalities between theta I, theta j over pi and theta k, theta l over pi, but it comes back to these elementary quadratic relations. And so if you have infinitely many special variety passing through your point, then you're forced to have some non-trivial elementary quadratic relations. Okay, so okay, now I want to explain a little bit how there is a natural conjecture which may be difficult, but maybe less difficult than Grothendieck periods conjecture related to this situation. So the way you prove that there is no Q-bar relations between the periods of a CM abelian variety is given by Wüstholz analytic subgroup theorem. So I will state it for CM abelian varieties, and I will try to give an analog in the case of Shimura varieties, or say the moduli space of abelian varieties. So when you have a CM abelian variety, you look at the uniformizing map from C power G to A of C, and you look also to the derivative of this uniformizing map, and you somehow you are saying that it's a way of relating the two natural BQ bar structure you have on the tangent space, because you go naturally from the first structure related to the lattice to the second structure related to the fact that your abelian variety is defined over Q bar. And if you choose correctly some eigenbasis for the geometric structure and the arithmetic structure, your differential, the differential map of uniformizing map is just the diagonal of, is just given by the diagonal matrix with entries, the holomorphic periods. And the theorem of Wüstholz is the following. So you start with a point at the level of C power j, the universal cover of A, and you assume that U of Z is a Q-bar point of abelian variety. Then you give yourself a subvector space of the arithmetic structure, so of Lie of A Q bar, and you assume that psi of Z is contained in V tensor C. So Wüstholz theorem is saying that the only explanation for this is that there is a subabelian variety which explains this situation. So there is an abelian subvariety B of A such that Lie of B is contained in V, and such that U of Z is contained in B. Okay. So it's a very, important result and working for all, say, commutative algebraic groups, but and its consequences of, any results on transcendence of the theta I, the holomorphic periods, are given or deduced from this result. So I'm saying that for Shimura varieties, you can try to mimic this situation. So if you have a connected Shimura variety, then you have a uniformizing map, and you have naturally the derivative of this uniformizing map, which relates the tangent space at a point of the Hermitian symmetric space to a point in the Shimura variety. So if you want to have a good theory, there is I mean, this is a bit more technical when you do the theory of Hermitian symmetric space, but you have to know that every Shimura, every Hermitian symmetric space has a realization inside the tangent space as a bounded symmetric domain. So the simplest case, if you want, is that for GL2, instead of taking the upper half plane, you take the unit disk. But yeah, in general, for example, you can have the unit ball in C power n associated to UN1, or I will describe for abelian varieties, maybe a moduli space of abelian varieties, but it's very important to work with the Harish-Chandra realization for the following reasons, which is not true if you don't work with this kind of realization. So when you look at the maximal compact associated to your point inside G of R, you look at its action on the Harish-Chandra realization, the bounded realization, then this action is linear. So you can think, if you use say Ziegler upper half plane, you never have some linear action. And also the sub-Shimura varieties, or the sub-symmetric bounded symmetric domains, are very simple. They are given by linear equations. So any bounded symmetric subdomain passing through the point O is just given by the intersection of its tangent space to D prime intersected with the bounded symmetric domain. So somehow at the level of the Shimura variety, it's very complicated to understand how a Shimura variety, a sub-Shimura variety is. But at the level of bounded symmetric domains, it's just a linear situation. So things are much more easy when you work at this level. But okay, so
I'm sorry.
yes.
The Shimura, the Harish-Chandra realization depends on the point O that you chose, right?
Always, yeah. You have one for each point.
Okay.
Okay, and so you can mimic the analytic subgroup theorem, and I call it hyperbolic analytic subspace theorem. So this, okay, what we hope is that if you start with an element Z in the bounded realization D, such that the image of Z in the Shimura variety is a Q-bar point of the Shimura variety. And if you look at a subvector space of the tangent space at the Shimura variety at this CM point, and you assume that when you take the derivative of a uniformizing map U that you call psi, you're inside V tensor C. So you could hope that somehow it has to be explained by a sub-Shimura variety, but in general, we believe that it's explained by some B-Q-bar subspaces. Not, and the only way should be that the vector space V contains some psi of V prime for some B-Q-bar vector subspace of the tangent space containing Z. And we hope that if the Mumford group is maximal, so somehow in this case you expect that there are no relations at all between the holomorphic periods, then this V prime should correspond to the tangent space of a sub-Shimura variety containing Z and the origin. Okay, so I should say that it seems to me that it's very hard to prove, and I mean, I made no progress on this conjecture, but I could just say that maybe it's easier than the Grothendieck period conjecture, and so.
Just can you give an interpretation in the case where we have a Shimura surface? If you've got a
I'll give the intersection for the moduli space of abelian varieties.
Okay.
Which is, I think, the only case you would be really interested in. So in the Siegel case, the bounded realization is given by matrices with coefficient in C, but which are still symmetric, but with the property of the identity minus identity is bigger than transposing of Z bar Z. And in this situation, you can find some basis of the tangent space at of the point above the CM point to the tangent space of to AG at the CM point, and it's just given by a diagonal matrix with entries the theta I, theta j divided by pi. So this is Kodera-Spencer theory somehow, and a consequence of the hyperbolic analytic subspace conjecture, which can be very hard to prove, is that you can deduce from this statement that there are no other quadratic relations between CM periods. The only ones are the elementary ones. And if, moreover, you're in the situation where the Mumford group is maximal, then you expect that you have no trivial quadratic relations between the holomorphic periods of A. So somehow it seems to be a very difficult conjecture, implying a very small part of Grothendieck period conjecture, but still, okay, it's a kind of different way of trying to advance in these ideas. So I will come back a little bit later to this, but I would like to explain the first theorem a little bit more, how it works, and how you somehow see that all the algebraic relations you are expecting among the periods of a CM abelian variety are given by these elementary quadratic relations. So I will define the notion of a Weil abelian variety of CM type. So when you have a CM field, say of dimension 2G over Q, it's very easy to see that the Galois closure, the Galois group of EC over Q, the Galois closure of E, is a subgroup of the Weil group Z over 2Z power G, semi-direct product SG. And we say that a field, a CM field is of Weil type is if this Galois group is maximal among the possibilities. And it's really, you have to think that it's more or less a generic situation. In general, it's the kind of thing that appears. So when you have a CM type, a decomposition of ohm E of C as the sum of two disjoint subsets, which if you have one embedding in one set, the conjugate is in the other. And so I'm just defining what is an abelian variety of Weil type. It's just an abelian variety associated to a couple E and a CM type phi E with E of Weil type. And I will not be interested in Weil type abelian varieties because in this case, the Mumford group of a Weil type abelian variety is in fact maximal. And so in this kind of situation, the Hodge conjecture is known for this kind of abelian varieties, and you don't expect any algebraic relations between the periods of such variety. But the interesting thing is that associated to such abelian variety, you can construct the reflex abelian variety. So when you have a CM field and a CM type, you can associate a reflex field of this CM field and CM type, and you can associate a reflex associated abelian variety. And so we say that an abelian variety A Church is of anti-Weil type if it's the reflex of a Weil type abelian variety. So the point is that if you have an abelian variety of anti-Weil type, then the dimension of this abelian variety is 2 power G minus 1. And there is a very natural isomorphism between the Mumford-Tate group of A and the Mumford-Tate group of AHH. And so the Mumford-Tate group of HH is very small. It cannot be smaller. In this situation, you expect a lot of relations between the algebraic relations between the periods, because you know that there is a bound on the transcendence degree of the relations between periods, which is given by the dimension of the Mumford-Tate group. So from Hodge theory, it's much more interesting to look at the anti-Weil type varieties. And so I try to explain a little bit how it works. So the dual HH is contained in EC, and the Galois group of EC to divide by HH is the symmetric group SG. And so if you look at the homomorphism of HH in C, okay, you can realize that it's the Weil group divided by SG, and this is isomorphic to Z over 2Z power G. But the best way of thinking about this is that it's isomorphic to the set of subset of 1G. And if you think in this way, a CM type on each edge is a collection of subset of 1G. And in fact, when you do the computation, the CM type is just the subset of 1G that do not contain the element 1. Okay, so you have to compute this. And so the periods, the holomorphic periods of HH are indexed by the subset of 1G, and the holomorphic periods of HH are theta I with one knot in I, and you always have these relations that theta I times theta I complementary is 2I pi. Okay, so the statement in this case is quite a nice combinatoric. So you have a lot of relations of the form theta I, theta j equals theta k, theta l. And the way you have this relation is if and only if the union of I and G is the union of K and L, and the intersection of I with G is the intersection with K with L. So it's very simple combinatoric. You can check you can deduce from this that the Q-bar space generated, I mean, the field generated by all the periods are in fact the field generated by G plus 1 of these periods. And you can take the period associated to the empty set, the period associated to the set with the element 1, the period associated to the element G. And somehow you expect to have you expect that there is no other relations because you think that the transcendence degree of this set of periods should be G plus 1. And you have naturally G plus 1 holomorphic periods. So, okay, so okay, you have several, we gave 2 proofs of this, and okay, you have to enter a lot, much more in the Hodge theory of CM abelian varieties, but it's really you can explain all the Hodge theory of CM abelian varieties by some linear algebra, and when you can compute fully all the Hodge tenses on CM abelian varieties, and you do the computation in this case, and you find, okay, it's really simple linear algebra, but a nice combinatoric. So another way that I like is the following. So you have this point which correspond to HH, so an anti-Weyl point in A 2 power G minus 1. And so what we do is for any quadruple of subset of 1G satisfying the previous condition, we construct a Shimura subvariety Z associated to this 4 subset of 1G. So not really in a 2g minus 1, but in a m times 2g minus 1, containing the point, the origin you started with m times, the product m times, and the fact that this sub-Shimura variety exists. First, I mean, you look at this tangent space, and it's a BQ bar subspace, and you check that it forces the equality theta I, theta j equal theta k, theta n. So you have an algebraic way of finding this equality. And from if you knew the Hodge conjecture, the Hodge relations that we were able to find would be explained by some algebraic subvarieties of powers of A. But here you find something geometric explaining the same relations. So I have to finish quickly. Yeah, in general, when we start with any abelian variety, we define something which is called generalized antivile. And okay, what I can say is that any simple CM abelian variety is a factor of some generalized antivile CM abelian variety of the form A cross B. And for A cross B, the computations of the Hodge ring is the same as the computation in the antivile situation I had before. So just to say a word, when you have a CM field of degree 2G, then the Galois group of EC over Q is smaller and contains in the Weil group Z over 2Z power G cross SG. And the set of CM types on E is identified to Z power 2Z power G, or the set of subsets of 1G. And you construct a CM algebra by looking at the geomorphism of this set S in EC, and you see that the S is also the homomorphism of this OMG of SEC in C, and you can construct phi is a CM type on X, and X phi defines an isogenic class of CM varieties, and you call this generalized antivile CM abelian varieties. So the point there is that all the computations I made in the antivile case from Hodge theory is exactly the same for this kind of abelian variety. But now any abelian variety of CM type is a factor of a generalized antivile CM abelian variety. So somehow it's exactly is the proof of the theorem 1 I gave. So I should stop here, I think. Thank you.